Hello and welcome to this episode. My name is Emad and I'm from Dana Company. It's a pleasure to have you with us. In this episode, I'd like to invite you into a fascinating conversation between two of my colleagues, Sarah and David, as they explore one of the most important questions of our time. What is artificial intelligence? So sit back, stay curious, and join us as Sarah and David break down the ideas, myths, and realities behind artificial intelligence and where it's all heading next. Let's begin.
Right now, at this exact moment, the very same underlying mathematical algorithms that are quietly guessing what word you're going to type next in a text message, well, they are simultaneously being used by scientists to fold complex proteins.
Yeah, it's pretty wild to think about. They're mapping the seafloor and, discovering entirely new classes of antibiotics using those same models.
Right. The underlying logic of your smartphone's autocorrect has, in a shockingly short amount of time, essentially become the math of human survival and scientific breakthrough. And yet, if you look around, everything seems perfectly normal.
Oh, totally normal.
You wake up, your alarm pulls you out of a light sleep cycle because it's been tracking your micro movements all night. Your email client has already quarantined the spam, flagged the urgent messages, and even generated, 3 possible one-sentence replies for you to just tap.
Saving you a few seconds here and there.
Exactly. And your car's navigation system has silently analyzed the GPS telemetry of 10,000 other drivers ahead of you on the highway. So it's seamlessly routing you around a traffic jam that hasn't even technically formed yet.
It is the ultimate invisible infrastructure. We are essentially living inside a matrix of constant, silent computation. And what is really fascinating to me is how quickly human psychology just adapts to this.
Oh, for sure. We just take it for granted.
We completely do. You don't think of the navigation app as this astonishing breakthrough in predictive modeling. You just get annoyed if it routes you through a red light.
Yeah, you're like, why is this stupid thing making me turn left here?
Right, exactly. But that seamlessness, that sort of frictionless integration into your daily life, it really masks the reality of what is actually happening. We are interacting with artificial intelligence dozens, maybe hundreds of times a day.
It's everywhere.
It is. It's a technological paradigm shift that is entirely on par with the discovery of electricity or the creation of the internet. But unlike electricity, which just powers our machines, this technology fundamentally alters how those machines process reality.
Which brings us to the core mission of this deep dive. Because you know the basics, you read the headlines, you know what these platforms do, and you likely use them in your workflow.
Hopefully you do, yeah.
Right. But the actual mechanisms, the how and the why, they are still treated like a black box by most of the public. If you ask the average person what is actually happening inside a large language model when it writes a poem, or how a piece of software actually learns to spot a tumor in an X-ray, the answers get very fuzzy very quickly.
They do. People just sort of gesture at the computer and say, well, it's an algorithm.
Exactly. So we want to rip the lid off that black box today. We are going to trace the actual mechanics of artificial intelligence. We're going to dive into the architecture, the history, the staggering mathematical breakthroughs, and honestly, the very real architectural limitations that the headlines tend to ignore.
And to do that properly, to really understand what it means to build artificial intelligence, we have to start by holding up a mirror.
Okay, what do you mean by that?
Well, we cannot understand the artificial component until we rigorously deconstruct the intelligence component. And this is where a lot of our cultural assumptions lead us completely astray.
How so?
When we use the word intelligence in everyday conversation, we usually fall back on a very narrow, highly industrialized definition. We think of rote memorization. We think of the person who can instantly calculate a massive math problem in their head, or the student who scores in the 99th percentile on a standardized test.
Right, yeah. We equate intelligence with a spreadsheet, basically. If you can store a massive amount of data and retrieve it instantly, you're deemed highly intelligent. But that is such a brittle, fragile way to look at cognitive capability. Think about the sheer spectrum of what the human brain actually does on a daily basis. You have a physician who can look at a patient, synthesize a dozen incredibly subtle, seemingly unrelated physical symptoms, factor in the patient's tone of voice and posture, and intuitively diagnose a rare autoimmune disease.
That's a perfect example.
Or think about a pilot. When an engine fails at 30,000 feet, that pilot isn't just recalling a manual, they are managing fear, assessing spatial orientation, processing the physical feedback of the yoke in their hands, and making life or death decisions in a fraction of a second in an environment they have never literally practiced in.
Right. Or even consider the arts. Think about a composer taking the abstract, highly subjective experience of human grief or joy and translating that into a mathematical arrangement of acoustic frequencies.
Wow, yeah, music.
And that music can induce tears in a listener who speaks an entirely different language. Each of these scenarios represents a profound, staggering display of intelligence, but the underlying cognitive mechanisms look completely different from one another.
It's not just one thing.
Exactly. And this highlights the first major hurdle researchers faced. Intelligence is not a single isolated process. It cannot be reduced to a solitary metric. But if we want to distill it down to its most functional, foundational definition, cognitive scientists generally point to one overriding capability.
Which is?
Adaptability. Intelligence is fundamentally the ability to adapt successfully to novel, previously unencountered situations.
Which brings us to an example from the source material that is just perfectly illustrative. A toddler taking their first steps. We look at that and think, oh, that's just a biological milestone. We don't view it as a high-level cognitive achievement.
Yeah, we just clap and take a video.
Right. But mechanically, what is happening in that child's brain is arguably more complex than a supercomputer playing chess.
Oh, it is vastly more complex. I mean, think about the physics involved. The toddler is attempting to balance a heavy, top-heavy physical structure on two small points of contact while navigating gravity.
It's basically a physics miracle.
It really is. To do this, their brain is processing a torrential flood of sensorimotor data. The vestibular system in the inner ear is constantly calculating spatial orientation. Proprioceptive sensors in the muscles and joints are feeding back the exact position of every limb. Visual data is streaming in to assess the distance to the coffee table.
And the toddler doesn't have an instruction manual. They don't know the equations for Newtonian physics.
Exactly. They're learning purely through iterative physical interaction with the world.
They take a step, their center of mass shifts too far left, they fall. And that fall isn't just a failure, it is a vital data point. The brain takes that physical pain, that sensory feedback, and adjusts the internal model. And so, okay, next time, fire the left calf muscle 3 milliseconds earlier.
Yes, every stumble is data. Every successful step reinforces the neural pathway. They are discovering the solution in real time through lived experience.
And what emerges from this process is sort of the holy grail of cognitive science, right? Transfer learning.
Precisely. This is what truly separates biological intelligence from narrow computation. Once that toddler learns to walk on a flat carpet, they possess a foundational model of balance and locomotion.
Right. They own that concept now.
And when they eventually encounter a grassy hill or a sandy beach or a staircase environments they have never seen before, they don't have to relearn how to walk from scratch. They extract the abstract principles of balance and forward momentum they learned in the living room, and they seamlessly apply them to the new, noisy, uncertain environment. They transfer the learning.
So it's not about having a pre-programmed response for a sandy beach. It's about having a dynamic, flexible model of the world that can stretch to fit new parameters. It's like intelligence isn't a single sharp blade, but a dynamic Swiss Army knife that constantly adds new tools to itself as you experience life.
I love that analogy. It's a self-building Swiss Army knife.
Right. But if intelligence is this messy, biological, incredibly fluid process, if it relies on having a physical body interacting with a physical world, how on earth did scientists ever look at a pile of silicon chips and wires and think, yeah, we can build that? Where do you even begin to bridge the gap between a biological toddler and binary code?
Well, you begin by breaking the problem down. If intelligence isn't just one monolithic thing, then the artificial recreation of it cannot be just one thing either. The goal of artificial intelligence, broadly speaking, is to engineer systems capable of performing tasks that traditionally require human cognition.
Right.
But to do that, the field had to splinter into highly specialized domains. We often use the analogy of a tree. The overarching discipline, the trunk of the tree, is AI. But the actual mechanical progress, the algorithms powering your daily life are happening out on the branches.
So let's climb out onto those branches, because this is where we have to stop talking about AI as a magic box and start talking about architecture. Let's start with the branch that actually powers almost everything we interact with today, machine learning. And to understand machine learning, we really need to understand why the old way of programming completely failed.
Precisely. Because for the first few decades of computer science, the paradigm was symbolic. or rules-based programming.
Basically just coding if-then statements.
Exactly. If you wanted a computer to do something, a human engineer had to manually write explicit, step-by-step instructions for every possible scenario. If A happens, execute B. If C happens, execute D. This works beautifully for keeping a ledger of bank accounts or running a payroll system, because the rules of math are static.
But the physical world is not static. It is infinitely complex and noisy.
It is incredibly noisy.
Right. Imagine trying to write the explicit rules for recognizing a cat in a photograph. How do you define a cat in binary code? You might say, well, look for 2 pointy ears. But what if the cat's ears are flattened down? What if it's looking away?
Or what if it's a hairless cat?
Exactly. What if the photo is blurry or the cat is half hidden behind a couch? You would have to write millions of if-then statements to account for lighting, angle, and obstruction. And the moment you encounter a variation you didn't code for, the system just breaks. It's an impossible bottleneck.
That bottleneck is known in the field as the combinatorial explosion. There are simply too many combinations of variables in the real world to manually hard-code them all. So machine learning flipped the entire paradigm upside down.
Okay, how so?
Well, instead of a human programmer writing the explicit rules to process the data, what if we provide the machine with the data and the desired output and let the machine discover the rules itself?
So instead of telling it what a cat looks like, you show it a million pictures of cats and a million pictures of things that are not cats, and you essentially say, figure out the difference.
That's exactly it.
But mechanically, how does a machine figure it out? It doesn't have eyes. It just sees numbers, right?
Right. And this is where we get into the mathematics of optimization. Every image is just a grid of pixels, and every pixel has a numerical value representing its color and brightness. In traditional machine learning, the system runs those numbers through a mathematical equation.
Okay, so it's doing math on the pixels.
Yeah. And initially, the equation is essentially guessing randomly. It looks at the grid of numbers and guesses, is this a cat? Yes or no. When it guesses wrong, a mathematical function called a loss function calculates exactly how wrong the guess was.
The loss function. Okay.
The system then uses an algorithm to slightly adjust the internal variables, the weights and biases of its equation, to make a slightly better guess the next time.
It's basically an automated game of hot or cold. It makes a guess. You say cold, it tweaks the dial, it guesses again. You say getting warmer. But it does this millions of times a second across massive data sets, constantly tweaking thousands of internal dials until the equation reliably outputs the correct answer.
That is a brilliant way to phrase it.
Yeah.
And that leads directly to the most powerful sub-branch of machine learning, which is deep learning. If standard machine learning is tweaking a few thousand dials, deep learning is tweaking billions or even trillions of dials. And it does so using a structure inspired by our own biology, the artificial neural network.
Okay, this is the term everyone hears, neural networks. But it sounds a bit too much like sci-fi. It makes people think we literally built a biological digital brain in a vat or something. Let's ground this. What actually is a layer in a neural network?
An artificial neural network is essentially a series of mathematical layers stacked on top of one another. You have an input layer where the raw data enters, say, the millions of pixels of an image.
Yeah.
You have an output layer at the very end that gives you the final prediction.
Right.
But in between, you have what we call hidden layers. And this is where the magic of deep learning happens. As the data passes from one hidden layer to the next, the network is extracting increasingly complex, abstract representations of that data.
So in the context of our cat photo, the first hidden layer isn't looking for a cat at all, is it? It's literally just looking for mathematical anomalies in the pixel values that indicate a contrast in light. It's just finding edges, horizontal lines, vertical lines, diagonal lines.
Correct. The first layer just finds edges. Then it passes those edges to the second layer. The second layer combines those edges to look for simple shapes, circles, curves, triangles.
Okay, I see.
It passes those shapes to the third layer, which might combine them to recognize a texture, like fur, or a specific feature, like an eye or a paw. By the time the data reaches the 50th or the 100th layer, the network has built a highly sophisticated mathematical hierarchy of features that allows it to confidently output the probability that the image contains a cat.
That's incredible.
And the crucial element here is backpropagation. When the network gets it wrong at the end, the error signal is propagated backward through all those layers, adjusting the mathematical weight of every single artificial neuron that contributed to the wrong answer.
It's staggering when you realize it's just linear algebra and calculus stacked incredibly deep, iterating millions of times. And that specific application teaching machines to interpret visual data is the branch called computer vision, right?
Yes, exactly.
This is what allows autonomous vehicles to look at a chaotic intersection, identify a pedestrian, predict their trajectory, and apply the brakes. It's not magic. It's rapid, multi-layered matrix multiplication identifying patterns in pixel grids.
And while computer vision gave machines the ability to see the physical world, an entirely different branch was required to tackle an even messier problem: human language. This brings us to natural language processing, or NLP.
Oh boy, language.
Yeah, if you think the physical world is chaotic, human language is an absolute nightmare for a computer. We rely on heavy context, sarcasm, idioms, cultural references, and implied meaning. How do you teach a machine, which only understands binary ones and zeros, the difference between "I'm going to the bank to deposit money" and "I'm sitting on the bank of the river"?
Because to a hard-coded system, the letters B, A, and K are identical in both sentences. This is where we have to talk about vector embeddings. Because when I finally understood this, it completely changed how I view these systems. The engineers didn't teach the computer a dictionary. They basically turned language into geometry.
Geometry is the perfect way to describe it. In modern NLP, words are mapped into a massive, multidimensional mathematical space. Imagine a map, not with 2 dimensions like north and south, but with thousands of dimensions.
Right.
Words that frequently appear together in similar contexts in human writing are placed physically closer together in this mathematical space. So the vector, the numerical coordinate for apple, will be placed very close to banana and orange, but very far away from bulldozer or democracy.
So the machine doesn't know what an apple tastes like. It just knows its precise coordinates in this massive galaxy of language. And because it's math, you can actually do algebra with these words.
You can, yeah.
The classic example is, if you take the mathematical coordinates for the word king, you subtract the coordinates for man, and you add the coordinates for women, the resulting point in that multidimensional space lands exactly on the word queen. It captures the semantic relationship of gender and royalty entirely through spatial geometry.
It's brilliant engineering. But even with embeddings, earlier NLP models struggled with long sentences because they process words sequentially, one by one. By the time they got to the end of a long paragraph, they sort of forgot what the first sentence was about.
They lost the plot.
Exactly. This all changed in 2017 with a specific architectural breakthrough called the transformer.
Ah, the T in ChatGPT.
Exactly. The transformer architecture introduced a mechanism called self-attention. Instead of reading a sentence word by word from left to right, a transformer looks at all the words in a sequence simultaneously.
Oh, wow. All at once.
All at once. For every single word, it calculates an attention score that measures how strongly that word relates to every other word in the sentence. This allows the model to instantly grasp context. It knows whether bank refers to a river or a financial institution because the attention mechanism explicitly links it to the surrounding words like water or deposit.
And when you scale that transformer architecture up, when you train it on essentially the entire digitized text of human history, you cross the threshold into the branch that is dominating our current era generative AI, specifically large language models, or LLMs. We moved from AI that classifies things like this is a cat, this is spam, to AI that creates entirely new outputs.
Right. Generative AI represents a massive leap in utility. These models are not pulling pre-written responses from a database. When you ask an LLM to write a cover letter for a job in the style of Shakespeare, it is navigating that multi-dimensional latent space we just discussed.
Doing the geometry.
Doing the geometry. It is calculating word by word the highest statistical probability of what the next word should be, constrained by the parameters of the prompt you gave it. It is generating the text sequentially, on the fly, driven entirely by probabilistic math.
Okay, I have to jump in here and push back on this, because here's where it gets really interesting. You can explain the multidimensional space and you can explain the self-attention mechanism, but when I actually sit down and interact with one of these advanced models, it is incredibly jarring.
It is.
If I have a deep, nuanced conversation with an LLM about philosophy, or I ask it to write a deeply emotional poem about a lonely astronaut looking back at Earth, it spits out something so poignant, so resonant, that it genuinely feels like there is a ghost in the machine. It feels like it understands loneliness. Are you telling me that a model with hundreds of billions of parameters that can pass the bar exam and write poetry doesn't actually understand a single word it's saying?
I am telling you exactly that, and it is the most vital distinction anyone using this technology needs to make. We are highly social primates. Our brains are hardwired by evolution to project intent, emotion, and consciousness onto anything that communicates with us in a human-like way.
We anthropomorphize everything.
We do, but we must separate the appearance of intelligence from the mechanism of intelligence. The LLM does not possess consciousness. It has no internal subjective experience. When it writes that poem, it does not feel the ache of loneliness, and it has absolutely no conception of the physical vacuum of space.
So it's essentially the most complex game of Mad Libs ever constructed.
It is a statistical mirror.
Yeah.
It has ingested centuries of human writing about loneliness. It has mathematically mapped how humans describe isolation, how we use metaphors about vast distances, how we structure sorrowful poetry. It is synthesizing those patterns with astonishing precision. It is an illusion of understanding generated by computational scale. It's mapping the topography of our language, but it has no idea what the terrain actually looks like.
Wow. So if we strip away the illusion, if we recognize that the AI is just executing linear algebra and probability at a massive scale, it forces us to confront the ultimate comparison. How does this silicon-based mathematical optimization actually stack up against our carbon-based biological intelligence? We always hear this framing of man versus machine, the idea that they are becoming smarter than us. But smarter seems like the wrong metric entirely.
It is the wrong metric because the two systems arrived at their capabilities through entirely different evolutionary pressures. Human cognition, as we discussed with the toddler, evolved over millions of years for one primary purpose: survival in a hostile physical environment.
Right.
Our intelligence is inextricably linked to our physical bodies. It is shaped by hunger, fear, the need for social cooperation, and physical exhaustion. Artificial intelligence, conversely, was explicitly engineered in a sterile environment to achieve specific computational objectives. It is optimized to minimize a loss function.
All right. Which means they excel at wildly different things.
Let's talk about learning efficiency, because this is a massive biological advantage. We mentioned how an AI needs to see 1 million pictures of a cat to recognize one. But a human child can look at a picture book, see an illustration of a cat, maybe see a real cat crossing the street once, and they instantly possess the concept of catness.
Yes.
They can recognize a cat made of Lego, a cat in a cartoon, a cat with 3 legs. Why are we so incredibly efficient at learning from sparse data?
Cognitive scientists believe it is because humans come preloaded with immense evolutionary priors. We are born into a 3-dimensional world, and our brains are already wired to understand physics, object permanence, and spatial relationships.
So we have a head start.
A massive head start. We have inductive biases that allow us to generalize from a single example. Machine learning models, generally speaking, start as a blank slate. They have to learn the concept of edges, shapes, and textures from scratch, which is why they require oceans of data to map the statistical boundaries of a concept. But once that machine does learn the boundaries, the scale tilts entirely in the other direction. This is where AI's mathematical nature becomes terrifyingly powerful. It's the axis of speed, memory, and scalability.
Absolutely.
If I ask a team of human researchers to read 50,000 medical research papers to find a hidden correlation between a specific protein and a disease, it would take them years. They would get tired, they would lose focus, and their memory would degrade. Human memory is notoriously reconstructive. Every time we recall a memory, we accidentally alter it.
AI suffers from none of those biological constraints. It operates at the speed of electricity. It can ingest and analyze those 50,000 papers in minutes. Its memory, its weights and biases do not degrade because it didn't get 8 hours of sleep.
Right.
This is why AI is so transformative and feels like drug discovery and material science. It can navigate combinations of variables that exceed the capacity of human working memory by orders of magnitude.
Yet for all that processing power, AI stumbles on things that a 5-year-old finds trivial. There is a concept in robotics and AI called Moravec's paradox, which I find endlessly fascinating. The paradox is that high-level reasoning, like playing grandmaster chess or doing calculus, requires very little computation to automate.
Yes, exactly.
But low-level sensory-motor skills, like walking up a flight of stairs or folding a towel, require enormous, almost insurmountable computational resources.
Moravec's paradox perfectly illustrates the divide. Abstract logic and mathematics are very recent inventions in human history, evolutionarily speaking. But sensorimotor skills, vision, balance, physical manipulation have been optimized by billions of years of biological evolution across countless species. We take it for granted because it feels effortless to us.
Right.
The sources highlight this with a simple test of common sense. If I say to you, the glass fell off the table because someone bumped into it, you instantly understand the physical mechanics.
Yeah.
You know glass is fragile, you understand gravity, you know that physical impact transfers energy.
But the AI doesn't know any of that implicitly. It only knows that the word glass and the word fell frequently co-occur in its training data. It doesn't have an internal physics engine modeling the shattering of the glass. It lacks common sense because it has never existed in a physical body subject to physical laws.
And that lack of physical existence also dictates the nature of creativity. We ask AI to generate art and music, and the outputs are structurally stunning. But AI creativity is fundamentally combinatorial. It is mathematically interpolating between existing human-generated works in its latent space.
Just mashing things up.
Exactly. Human creativity is driven by tension. It is driven by mortality, by falling in love, by political outrage, by cultural history, and AI cannot create a truly subversive piece of art because it has no status quo to subvert. It has no skin in the game.
Speaking of having skin in the game, we cannot ignore the sheer physical cost of running these systems. Let's talk about energy efficiency because the contrast is frankly absurd. It blows my mind that your brain, which is simultaneously regulating your endocrine system, processing visual and auditory data in real time, accessing decades of memories, and engaging in this complex conversation, is running on roughly 20 watts of power.
It's amazing.
That is the energy required to power a dim light bulb inside your refrigerator. And it's doing all of that complex emotional and physical processing. Meanwhile, AI needs a whole power plant just to figure out how to draw a hand.
It really is the pinnacle of thermodynamic efficiency. Biological synapses run on incredibly low voltage, and the brain processes information in a massively parallel analog fashion. By contrast, the architecture we currently use for AI is wildly inefficient. To train a single state-of-the-art large language model, you're running tens of thousands of specialized GPUs at maximum capacity for months.
Just burning through power.
Exactly. You are consuming gigawatt hours of electricity. You are essentially requiring the power output of a small nuclear reactor to teach a machine how to accurately predict the next word in a sentence.
So when we stack it all up, the data hunger, the lack of common sense, the massive energy requirements, it completely reframes the narrative. It's not humans versus machines. It's a complementary relationship. We aren't building a replacement for human intelligence. We have engineered an entirely new alien form of cognitive optimization. AI brings speed, precision, and scale. Humans bring ethics, wisdom, context, and meaning.
It is a symbiotic relationship. But recognizing how different this intelligence is naturally begs a historical question. The algorithms powering this today are incredibly complex, but the foundational desire to build this didn't just appear when the microchip was invented. The philosophical roots of this go back significantly further.
Where did this even come from? Who woke up one day and decided to build this? Let's trace that history, because this didn't start in a Silicon Valley garage. The urge to create artificial minds is embedded deeply in human mythology. Long before we had silicon, we had stories.
We really did.
In ancient Greek myths, you have Talos, the giant bronze automaton forged by Hephaestus to patrol the shores of Crete. In Jewish folklore, you have the golem, an artificial being animated from mud and clay through mystical incantations to protect the community. Even in the Renaissance, Leonardo da Vinci drafted schematics for a mechanical knight operated by a series of pulleys and gears.
We have always been obsessed with the idea of playing creator, of mechanizing our own cognitive spark. But it remained purely in the realm of fiction and clockwork until the mid-20th century. The true paradigm shift required a fundamental change in how we viewed mathematics and logic, and that shift was largely driven by Alan Turing.
Turing is such a fascinating figure. Most people know him for his vital work during World War II, cracking the German Enigma code at Bletchley Park. He proved that a machine could rapidly sequence through permutations to find a solution faster than a human ever could. But his vision went far beyond code breaking, didn't it?
It did. He was asking much deeper philosophical questions about the nature of computation itself. Turing realized that a machine wasn't just a physical configuration of gears. It was a theoretical engine that could manipulate symbols according to logical rules. And in 1950, he published a paper titled Computing Machinery and Intelligence, which essentially launched the modern field.
Wow.
But the genius of Turing's paper was what he didn't do. He didn't try to define what thinking was, because philosophers had been arguing about that for centuries without resolution. Instead, he proposed a pragmatic, testable behavioral metric, which we now call the Turing test.
Right, the imitation game. He basically said, let's stop arguing about whether a submarine swims like a fish. Let's just ask, if a human judge is communicating via text with a machine in one room and a human in another, and the judge cannot reliably tell which is the machine, Well, then for all practical intents and purposes, we must concede the machine is exhibiting intelligence. He shifted the entire field from philosophy to behavioral engineering.
And that pragmatic framing provided the spark for what is widely considered the official birth of the field. In the summer of 1956, a young mathematician named John McCarthy organized a research project at Dartmouth College. He invited the brightest minds in early computer science people like Marvin Minsky, Claude Shannon, and Herbert Simon. McCarthy actually coined the term artificial intelligence specifically for this proposal to differentiate it from general computing.
And the hubris of this proposal is just legendary. You read the original Dartmouth proposal, and they explicitly state they believe that every aspect of learning and intelligence can be so precisely described that a machine can be made to simulate it. And they honestly thought that if a dozen of them just worked on it over the summer, they could make a significant breakthrough in natural language, neural networks, and problem solving. They thought human-level AI was just a generation away.
That supreme optimism fueled the initial boom. Throughout the late 50s and 60s, government agencies poured money into AI research. This was the era of symbolic AI we discussed earlier, trying to hard code logic. And in closed, controlled laboratory environments, they had early successes. They built programs that could solve algebra word problems or prove geometric theorems. The researchers claimed AI would soon perform any intellectual task a human could.
But then they hit reality. The real world isn't a geometry proof. They slammed headfirst into the combinatorial explosion in Moravec's paradox. They realized that translating a Russian document into English wasn't just swapping words from a dictionary. It required massive cultural and contextual knowledge that simply couldn't be hard-coded. The promises failed to materialize, the government funding completely dried up in the 1970s, and the field entered what became known as the first AI winter.
The AI winter is a crucial concept to understand here. It represents a cycle of massive hype leading to immense funding, followed by the realization of architectural limitations, leading to a total collapse in interest and capital. The field was essentially frozen for a decade. It only thawed in the 1980s with a new approach expert systems.
Right, so they gave up on building a general thinking machine and decided to build highly specialized idiot savants. They would interview a human expert, like a doctor, extract thousands of specific if-then rules from their brain and code them into a system. The most famous was MYCIN, designed to diagnose blood infections. And it actually worked. It was as accurate as human infectious disease specialists. Corporations saw the commercial potential, and the hype cycle started all over again.
But once again, they hit a structural wall. Expert systems were incredibly brittle. They had no common sense. If MYCIN was given data about a patient that fell slightly outside its rigid rules, it wouldn't just fail gracefully, it would output a confidently absurd diagnosis.
Oh, that's dangerous.
Very. Furthermore, maintaining them was a nightmare. If medical knowledge updated, human programmers had to manually comb through tens of thousands of lines of code to rewrite the rules without breaking the rest of the system. The maintenance costs far outweigh the utility. So the bubble burst again in the late 1980s, plunging the field into the second AI winter.
So what does this all mean? We basically suffered through cycles of massive hype and crushing disappointment. It's like the technology kept hitting a glass ceiling of its own design. They kept building higher and higher ladders, only to realize you can't reach the moon with a ladder. The entire underlying architecture of hard-coded rules was fundamentally flawed.
It absolutely was.
The real breakthrough, the one that ended the winters for good, required abandoning rules entirely. This was the shift to machine learning in the 90s, powered by the rise of the internet providing more data. And the cultural milestone of this era was 1997, when IBM's Deep Blue defeated the reigning world chess champion, Garry Kasparov.
Deep Blue's victory was a massive psychological shock to the public. Chess had always been viewed as a pinnacle of human intellect. But architecturally, Deep Blue was largely a triumph of brute force calculation. It could evaluate 200 million board positions per second. It didn't possess intuition. It just searched a mathematical decision tree faster than Kasparov could. The true algorithmic revolution, the actual shattering of the glass ceiling, came much later, driven by deep learning and neural networks.
And the undisputed turning point was 2012 with a neural network called AlexNet. There was this annual competition called ImageNet, where researchers tried to build software that could accurately identify millions of images. For years, the traditional hand-coded vision systems had flatlined, plateauing around a 25% error rate. Then, in 2012, a team from the University of Toronto unleashed AlexNet, a deep convolutional neural network. It didn't just beat the traditional systems, it obliterated them, dropping the error rate by an astonishing margin. It proved unequivocally that deep neural networks, given enough data and computing power, were vastly superior to human-engineered rules.
That moment triggered an avalanche of investment into deep learning. And just 4 years later, in 2016, the world saw an even more profound demonstration. Google DeepMind developed an AI called AlphaGo to play the ancient board game of Go. Go is exponentially more complex than chess. There are more possible board configurations in Go than there are atoms in the observable universe.
That is just incomprehensible.
It is. You cannot use brute force calculation to win. It requires what Go masters call intuition and long-term abstract strategy.
And AlphaGo defeated Lee Sedol, an absolute legend of the game. But it wasn't just that it won, it was how it won. In Game 2, AlphaGo played Move 37. It placed a stone in a position so counterintuitive, so bizarre, that human commentators literally thought it was a mechanical glitch. No human master would ever play that move. But the AI, having played millions of games against itself via reinforcement learning, had discovered a deeply alien, mathematically superior strategy that human history had completely missed. It was a terrifyingly brilliant display of non-human optimization.
And that trajectory from AlexNet to AlphaGo sets the stage for the modern era. The mathematical foundations for neural networks had actually existed since the 1980s. The ideas were there. But they lay dormant through the winters because the physical and digital infrastructure to support them didn't exist. So the question becomes, why did it explode now? Why did the 2020s become the era where AI broke out of the laboratory and infiltrated every single smartphone on Earth?
That is the multi-trillion-dollar question. The public perception is that some genius in a lab suddenly wrote a magic line of code in 2022, but the reality is far more industrial. The sources outline this beautifully using the analogy of a rocket launch. You can have the blueprints for the most advanced rocket engine in the world in 1985, but if you don't have refined rocket fuel, advanced metallurgy, and a global logistics supply chain, that rocket is never leaving the launch pad. The explosion of AI right now is not a single breakthrough, it is the simultaneous convergence of 6 distinct historical forces. Let's break down the launch sequence.
Let's do it. The first and most critical force is data, the rocket fuel. As we establish, neural networks are data-hungry architectures. They require millions of examples to adjust their internal weights. For decades, the AI community was starving for data. But then, the internet matured.
Yeah, we gave it to them.
Yep. Exactly. For 25 years, billions of humans actively digitized their lives. We uploaded trillions of photographs, wrote millions of Wikipedia articles, published endless blogs, and pushed countless repositories of code to the web. We inadvertently built the exact, massive, universally accessible training data set required to fuel large language models.
We were basically doing free data entry for the AI revolution without even realizing it. But force number 2 is just as vital: computing power. You have the fuel, but you need an engine capable of burning it. And this is where the history of technology gets delightfully absurd, because the computational savior of AI came from teenagers wanting to play better video games.
It really is one of the greatest technological accidents in history.
Yeah.
Traditional computer processors, CPUs, are very fast, but they process tasks sequentially, one after another.
Yeah.
This is terrible for neural networks, which need to do millions of small mathematical calculations, matrix multiplication simultaneously. However, in the late 90s and 2000s, the video game industry demanded increasingly realistic 3D graphics.
Right.
Rendering a 3D environment requires calculating the color and lighting of millions of individual pixels on a screen at the exact same time. To do this, hardware companies developed graphics processing units, or GPUs.
And it turns out that the exact hardware architecture designed to render the explosions in a video game at 60 frames per second is mathematically identical to the architecture needed to push massive datasets through the layers of a neural network. Without the gamers needing better graphics or the internet creating oceans of data, the brilliant algorithms from the 50s and 60s would have stayed frozen in an AI winter forever. AI researchers realized they could hijack GPUs for deep learning, and overnight, training models went from taking years to taking weeks.
Which unlocked the third force: algorithmic progress. With data and compute available, researchers could finally experiment rapidly. We saw the development of deep convolutional architectures for vision, and then crucially, the 2017 publication by Google researchers of the paper, "Attention is All You Need." This paper introduced the transformer architecture we discussed earlier. It proved that you didn't need complex sequential processing for language. You just needed self-attention mechanisms running in parallel across massive data. The transformer fundamentally unlocked the scalability of generative AI.
which acts as a massive beacon for the fourth force: investment. Once the tech industry saw the scalability of the transformer, the arms race began. We are talking about an unprecedented influx of capital. Tech giants, Microsoft, Google, Meta, and specialized labs like OpenAI and Anthropic began pouring tens of billions of dollars into securing computing clusters and hiring top researchers. This hyper-capitalized environment compressed what would normally be decades of steady academic research into a few frantic years of exponential scaling.
And all that scaling culminated in the fifth force, mass consumer adoption. For a long time, interacting with AI required writing code in a terminal. It was a tool for engineers. But in late 2022, OpenAI released ChatGPT, which wrapped a massive neural network inside a simple, intuitive chat interface. It utilized a technique called reinforcement learning from human feedback, having humans rate the AI's responses to make the model conversational, helpful, and aligned with human dialogue expectations. Overnight, AI went from an invisible back-end process to a highly visible, highly interactive utility used by hundreds of millions of people.
It was the Netscape Navigator moment for AI. The interface made the invisible technology tangible. But as incredible as the chat interface is, the sources point to a sixth force that is currently emerging, and this is the one that fundamentally changes the economy: the shift toward AI agents.
This is the frontier we are actively crossing. A standard large language model is passive. It possesses a vast, latent space of knowledge, but it waits for you to prompt it, and it outputs text. It knows things. An AI agent transitions from knowing to doing. An agent is a system where you provide a high-level goal, and the AI autonomously formulates a multi-step plan, writes code, browses the live internet, interacts with external software APIs, and executes the tasks iteratively, correcting its own errors along the way.
So we are moving from an incredibly smart encyclopedia that just talks to you to an actual digital intern that goes out and does the work for you. Instead of saying, write me an email template for a marketing campaign, you say to an agent, analyze my competitor's website, develop a counter-marketing strategy, draft the copy, generate the images, and schedule the emails in my marketing software. And the agent acts as an autonomous digital intern executing the loop. The productivity implications are staggering.
They absolutely are.
But, predictably, with this massive explosion in capability comes a massive explosion in public panic and confusion. When you drop a technology this powerful and autonomous into the laps of the general public overnight, the reaction isn't just awe, it's panic.
The anxiety is entirely warranted. The pace of capability overhang, the gap between what the technology can do and our societal ability to understand it, is massive. And unfortunately, the public discourse is severely polluted by decades of science fiction tropes and sensationalist tech journalism. We desperately need to separate the mechanical reality of the technology from the mythological fears surrounding it. We need to debunk the core myths.
And the most pervasive myth, the one we keep bumping into, is the myth of consciousness. The idea that these models are waking up, that they have an internal agenda, or that they secretly harbor ill will toward humanity.
Yeah.
When a model refuses to answer a question, people think it's being stubborn. When it gives a wildly incorrect answer, people say the AI is lying or gaslighting them.
Applying human psychological terms like lying to a matrix of weights and biases is a fundamental category error. A lie requires an understanding of the objective truth and a deliberate intent to deceive. An LLM possesses neither. It is navigating probability. This perfectly explains the phenomenon known as hallucinations. When an AI invents a fake legal precedent or confidently explains a historical event that never happened, it hasn't lost its mind. It has simply traversed a pathway in its latent space where the statistical probability of the next word happening to form a coherent but factually false sentence was very high. The model doesn't know the difference between a factual Wikipedia article and a piece of fantasy fiction it ingested. It just maps the linguistic geometry.
It's mathematically doing exactly what it was designed to do, predicting text. It just happens that the math doesn't align with reality. But a myth that is grounded in very real anxiety is the fear of total job replacement. The prevailing narrative is that AI is going to automate all cognitive labor, leaving humanity utterly unemployed and adrift. If the AI agent can do the research, write the code, and draft the briefs, what exactly is left for the human being to do? Okay, history tells us work gets redistributed, but hasn't this transition always been incredibly painful for the people living through it? If AI is doing the thinking, what kind of new jobs are even left for us?
It is the most urgent socioeconomic question of our time. But looking at the history of automation provides critical context. Technological revolutions, the mechanical loom, the steam engine, the spreadsheet, rarely eliminate human labor entirely. What they do is automate specific tasks within a job, not the entire complex occupation. When the electronic spreadsheet was introduced, people thought accountants were obsolete. Instead, it eliminated the drudgery of manual calculation, allowing accountants to focus on higher-level financial strategy. It vastly expanded the industry. AI will likely follow a similar path of redistribution and augmentation.
But the disruption is real and immediate for those affected right now.
The disruption is absolutely real, and it will require massive societal adaptation. But the functional reality for individuals right now is not humans being replaced by AI. It is humans who refuse to use AI being replaced by humans who master it. The defining professional skill of the next decade is collaboration with these systems. A radiologist using AI to flag microscopic anomalies can review scans significantly faster, allowing them to spend their time actually communicating with patients, interpreting the holistic medical context, and making nuanced ethical decisions. The jobs that remain will lean heavily into the things AI lacks: emotional intelligence, complex physical manipulation, and high-level strategic oversight.
Which brings us to the most dangerous myth of all, the assumption of algorithmic objectivity. There is deep-seated human bias that math is neutral. If a computer spits out a decision, we assume it must be objective, fair, and free of human prejudice. But the AI is just a mirror, and the data it was trained on is us.
And our historical data is structurally flawed. This is a purely mathematical problem of dataset distribution and sampling errors. If you train a machine learning model to filter resumes for a software engineering role, and you feed it the historical hiring data of the tech industry from the last 30 years, the math is going to quickly notice a statistical correlation. Historically, a high percentage of successful hires in this dataset were male. The algorithm, optimizing for past success, will mathematically penalize resumes containing words associated with women. It doesn't hate women. It is blindly optimizing based on the skewed mathematical weights of our own historical inequalities.
So the model inherently replicates and automates the biases baked into the training data. If the word doctor frequently co-occurs with he's in historical text, the vector embeddings will physically position those concepts closer together in the latent space. We aren't building a perfect objective oracle. We're building a high-speed reflection of humanity's past, flaws and all. And that requires intense human oversight, rigorous auditing of training data, and a deep understanding of how these statistical pipelines actually function.
Precisely, which dismantles the final misconception. The idea that AI is some distant future problem, something we can worry about a decade from now when the robots walk down the street. It is not the future, it is the immediate present. As we established right at the start, it is already the foundational layer of our modern digital infrastructure. The decisions it makes based on those statistical weights are already determining who gets approved for a mortgage, how medical resources are allocated, and what information reaches your social media feed.
It's already here. And looking back at the massive journey we've taken today, it is genuinely staggering to see the scope of this evolution. We started with the toddler learning gravity, traced the philosophical dreams of ancient myths, walked through Turing's pragmatic behavioral tests, and witnessed the hubris of the Dartmouth Conference. We saw the field freeze during the winters of brittle, hard-coded rules, only to spectacularly shatter the glass ceiling when data, video game GPUs, and deep neural networks converged.
We moved from an era of telling computers exactly what to do to an era of giving them data and letting them discover the patterns themselves. We've mapped human language into multi-dimensional geometry and witnessed the rise of autonomous agents. But the central takeaway, the through line of all this technology, is that AI is neither a magical entity nor an apocalyptic monster. It is a powerful, highly sophisticated computational system. It is an optimizer of functions.
It is an alien form of intelligence, fundamentally different from our own biological lived experience. And because it is a tool, its ultimate impact on our civilization doesn't depend on the math itself. It depends entirely on the wisdom, the caution, and the intent of the humans wielding it.
We are the architects. The models will only optimize for the objectives we specify, using the data we provide. Our responsibility is to ensure that this extraordinary mathematical capacity is aligned with human flourishing.
To close out this deep dive, I want to leave you with one final, slightly provocative thought to turn over in your mind. We spent a lot of time today talking about how our human intelligence was forged by the brutal constraints of biological survival in a physical world. Our brains are tied to our bodies, our mortality, and our physical limits. But artificial intelligence is evolving at a breakneck, exponential pace in a domain made entirely of digital data. It has no biological constraints, it doesn't need to sleep, it doesn't fear death, and it isn't bound by 20 watts of energy. As it continues to scale, completely free from the evolutionary pressures that created us, what kind of entirely alien cognition might it eventually become? And perhaps even more importantly, as we continue to intertwine these systems with our daily lives, how will it fundamentally alter us when our ancient survival-driven biology fully merges with its limitless, untiring mathematics? Thank you so much for joining us on this exploration. We hope it helped illuminate the invisible infrastructure around you. Keep questioning the technology, stay intensely curious, and we will catch you on the next deep dive.